Hello everyone and welcome to the channel CSAI TTL Think to Learn. Today we are going to discuss the golden rule of database architecture. Bring the competition to the data, not data to the competition. Data locality isn't just a switch you flip. It's a foundational design decision. Before we jump in, please smash that like button, subscribe and share this video with your engineering team. Also, head over to bitbytoken.com after you watch this video, your ultimate resource for foundational concepts and deep dive system design guides across software, data, AI, and machine learning engineering. We have we have tried to aim to bring a lot of details to this software engineering and different related concepts. Here you can actually look by the fundamentals. You can search. Each of the fundamentals are further subdivided into basics, advanced, and experts. Along with these, we have sample example solutions which you can cover. Designing WhatsApp, Instagram. Each of these we try to gain through FR and FRs. Then further we go to the data model. Um, you can also look at different, let's say, the sequence diagrams available for all of these are different. And we further discuss the horizontal scaling, database sharding, and various concepts related to specific solution for each of these. Do look into this and provide your feedback on how we can make this site better and any other topic that you would want us to incorporate in this site. Okay, let's get to our topic now. All right, let's start with the root anti-pattern. If you execute a query that requires scanning 500 million rows just to filter a single region, you're creating IO waste on a catastrophic scale. Your data is nowhere near the computation that needs it. This is a design flaw, and today we are going to show you how to fix it. Partitioning is your first line of defense, organizing the single disk. We aren't moving server, we are just installing proper shelving. By using range partitioning, we physically group data by intent, like storing 2023 orders together. It's simple, it's effective, and drastically reduces the data your database need to touch. Under the hood, this works through partition pruning. The optimizer knows exactly which file to open before the execution even starts. But watch out for the anti-pattern. If you wrap your partition key in a function like year or a date column, you break the optimizer. It can't see through the function, so it defaults to a full table scan, and your performance goes out of the window. When choosing a strategy, compare vertical and hash. Vertical partitioning pulls cold columns like huge image blobs out of the hot path so your CPU and RAM aren't wasted dragging that data around to check a simple price. Meanwhile, hash partitioning is a master of perfect distribution and eliminating hotspots, though it does sacrifice data locality for range queries. Eventually you hit the scale ceiling. Partitioning is an intra-database technique. It lives inside one box. If your CPU is pegged at 100% or your disk IO is saturated, you simply cannot add more RAM to that physical server. When vertical scaling dies, horizontal scaling begins. This leads us to sharding, opening branch libraries. Now we are operating across physical boundaries. We have independent database instances, each with its own CPU and memory. If one server goes down, the rest of your system remains completely untouched. It's true isolation. But you have to respect the speed of physics. Accessing local memory takes 100 nanoseconds, while a cross-region network call can takes 80 milliseconds. That's a 1 million x difference. Locality isn't just an academic optimization. It is literally the difference between a lightning fast experience and a sluggish, broken system. Our biggest enemy is the cross-shard join. This is the scatter-gather anti-pattern. If your data is scattered, the system has to pull rows from three different servers and stitch them together over the network. It's slow, it's resource heavy, and it should be avoided at all costs. The antidote is co-location. If related data travels together, like a user's profile, their friends list, and their post, you should share the same shard key. Keeping them on the same physical metal is the single most important locality optimization you can make. However, beware of the hotspot problem. If you co-locate everything perfectly, you create a target for the viral influencer scenario. If one user goes viral and has 50 million followers, that one shard will melt down. Perfect locality can sometimes lead to terrible balance. How do we resolve this? Dynamically. Modern databases like Spanner and CockroachDB prefer range-based sharding internally because it allows them to split a hot shard into two smaller chunks on the fly. They can then divert read traffic to new clones, fixing the hotspot without a total system restart. For unpredictable growth, we use consistent hashing. Naive modulo hashing forces you to migrate almost your entire dataset when you add a node. Consistent hashing, however, maps everything to a circular ring. So adding a node only remaps the minimum number of keys. It's the elegant middle ground for growing systems. This is the layered architecture. Sharding at a server level, co-location at the relationship level, and partitioning at the disk level. Modern systems use all three. They aren't in different concepts. They are the same idea of data locality expressed at different granularities. To wrap up, use this system design cheat sheet. Analyze your access patterns, look at your cardinality, plan your joins, and prepare for growth. The fastest system don't have the cleverest code. They have the data exactly where the computation expects it. What's the biggest scaling mistake you have seen? Tell us in the comments below. If you enjoyed this series, please like, subscribe, and share. And I'll see you in the next one. Thanks.